Dear colleagues, my presentation about the problem of rigorous specification and analysis of distributed system behavioral constraints. I need to say that the presented research is a part of studying causality relationship in distributed systems carried out jointly by the Department of Theoretical and Applied Computer Science at Karazin, Kharkiv National University, and research team Kairos from National Research Institute of Informatics and Automatics in Ria, France. At the beginning of my presentation, I want to clarify what we understand as a distributed system. Our understanding is the same as the understanding given by Andrew Tannenbaum and Martin van Steen in their well-known monography, Distributed Systems, Principles and Paradigms. So, a distributed system consists of a set of components located on different nodes of a network. These components interact with one another by exchanging messages for achieving the common goals. Tannenbaum and van Steen determined three significant features of distributed system, namely concurrency of their components, lack of a global clock, and independent failure of components. For each project, this feature turned the achievement of a common goal by the system components into a non-trivial problem for engineers developing the system. We need to stress that modern complex technical systems are distributed ones, and they are neither purely cybernetic nor purely physical. Hence, we come to the concept of the cyber-physical system, covering a large class of modern technical systems, including, for example, Internet of Things. For systems of this class, the behavioral correctness is critically important because incorrectness can lead to an essential negative impact on systems surrounding. The concept of cyber-physical system was given by USA National Science Fund. At the slide you can see the definition of the concept and hyperlink to the corresponding source. This concept covers a variety of distributed systems such as smart grids, autonomous automobile system, medical monitoring systems, industrial control systems, robotics systems, and automatic pilot avionics systems. Summing up this review, we can claim that the key problem for developing distributed system is specifying and analyzing the correct system behavior based on the observable system events. The important conclusion of this claim is understanding the necessity of reliable tools for specifying and analyzing behavioral constraint, and primarily the corresponding language tools. Our research is based on the assumption that behavior of a distributed system is described by the discrete dynamics of a suitable kind. At this slide you can see two kinds of dynamics, namely the discrete dynamics and the discrete dynamics with output. Their difference consists in the different observation possibilities. For the discrete dynamics, we have no possibilities of observing system states. In this case, a system has trajectories, but these trajectories cannot be observed. This is the simplest but not an interesting case. For the discrete dynamic with output, we also have no possibility to observe directly system states, but we have a possibility to observe notifications sent by the system. This case is very interesting in the context of our research. Later we will consider other kinds of discrete dynamical systems related to our research. But these examples show that we need in some general mathematical theory covering a wide class of discrete dynamical systems. The corresponding mathematical framework was proposed by Jan Rutten in his fundamental paper, Universal Coalgebras, a Theory of Systems, published by Journal Theoretical Computer Science in 2000. The main idea of Rutten is to consider a discrete dynamical system as a mapping from its state space into this space wrapped into the verb specific for the considered kind of dynamics. The additional advantage of the idea is that the construction can be realized for an arbitrary category, not only for category of sets. From the definition of a coalgebra, one can see that specific of the state space, the carrier of a coalgebra, is defined by the underlying category, and the wrapping is defined by the endofunctor of this category. This definition of a coalgebra leads naturally to the following definition of a coalgebraic morphism. The manner for defining coalgebraic morphism is usual for category theory. Thus, the following theorem is quite natural. One of the key instruments in coalgebra theory is the concept of final coalgebra, which the definition is presented at the slide. The importance of a final coalgebra is determined in the fact that it gives a method to associate uniquely a morphism into itself from any coalgebra. Such a morphism called an anamorphism. Another key tool for studying coalgebras is the concept of bisimulation. Informally saying, two coalgebras are bisimilar if they have the same set of dynamics invariants. Coming back to the origin of our consideration, one can understand that coalgebras are good models of different kinds of dynamics. The next several slides demonstrate how the coalgebraic language can be interpreted for different kinds of discrete dynamics. The first example considers the simplest case, namely discrete dynamical systems. I need only say that the triviality of the systems is defined by the triviality of the corresponding final coalgebra. The less trivial example is given by systems with termination. In contrast to the previous example, a system of this class cannot continue operating if it has reached some distinguished state. There is a final coalgebra for this category of systems. Its structure is shown at the slide. Another important category of system is the category of systems with output. Coalgebra from this category are models of system components in the proposed approach. One can see at this slide that the wrapping endofunctor for this case provides sending the corresponding notification under each system state changing. It is very interesting that in this case the carrier of the final coalgebra is a set of notification streams, and the image of any state under the action of anamorphism coincides with the stream generated by the system if this state is the initial state of the system. Our next example is principle for the studying. The structure of wrapping endofunctor for this case allows to get a notification and to recognize whether this notification is acceptable at the current system state or no. In other words, coalgebra of this category can be used as detectors of system behavioral violation. The structure of final coalgebra in the corresponding category of coalgebras is not simple, but it is presented in details at the slide. Here you can also see the structure of anamorphism. Now we are ready to give the principal construction of our research. This construction is a befunctor, combining two systems, a system with outputs with a detector, into a system with termination. The definition of actions the befunctor on objects and morphisms presented at the slide. Saying informally, befunctor join gives a tool for for monitoring a system stream to identify its violations. It is a principally important fact that these actions are determining the befunctor as established by theorem about functoriality of joining. Theorem about preserving bisimilarity is very useful because it establishes the possibility to change any system by bisimilation before joining without changing the bisimilation class of the resulted system with termination. Now we can formulate the main result of the presented study. It is the following. There is a correspondence associating detectors with set of notification streams. Moreover, this correspondence allows using only set representing so-called safety constraints. Informally saying, a safety constraint is a constraint that can recognize a violation of any stream using information about some initial segment of the stream only. This notion was introduced by Leslie Lamport. At this slide, the corresponding formal definition given by Alpert and Schneider is shown. This slide demonstrates how the mentioned association can be built. To do this, we need a special coalgebra with output. Any such a coalgebra is associated with a stream, how it is specified by the first equation at the slide. Now, if we have some detector, we can use befunctor join for obtaining the corresponding system with termination. Finally, the anamorphism of this system gives a possibility to determine whether the combined system can fail or no. For a given detector, we consider as correct only such a stream that belongs to stream set determined by the second equation at the slide. The theorem proved in our work, which you see on the slide, establishes the fact that the class of safety constraint is exactly the class of constraint recognized by the detectors we defined. From the presented results, theorem about universal detector follows easily. We need only to use theorem about preserving bisimilarity. Theorem about universal detector allows concluding the following. Firstly, the final detector is a universal detector. Secondly, carrier points of the final detector, i.e. prefix-free sets of finite sequences of notifications, are the tools for specifying safety constraints. Taking into account the last remark, we can pose the problem to understand how different classes of prefix-free languages, for example, regular languages, context-free languages, and so on, can be used for classifying detectors. Also, it is very interesting the construction of compositional theory for detectors. Finally, the problem defining and estimating complexity of recognizing violation is very important from the practical point of view. Thanks you for your attention.